Hello class, this is Professor Feynman. In today's lecture, we're going to take a second look at the linear least squares derivation for the simple linear model case, so the y equals ax plus b case. But we're going to use a concept called sum of squares. And so first, let's define what are sum of squares. And so whatever we're dealing with a data set and then the sample means, we can define the sum of squares of the input, the x variable, is just the summation over the whole data set of each datum minus the mean, and then we square it. So it's the sum of squares. And we can rewrite this summation as it's actually the summation of xi squared minus the number of data points times the mean squared. And then so the formula for the sum of squares of the output variable y, it has the same format, but we just replace x with y, yi minus y bar squared, and that's yi squared minus n times y bar squared. Then we have the sum of squares of xy. And here now we have, it's kind of like a quadratic term. It's the summation over I of xi minus the mean of x times yi minus the mean of y. And then we can rewrite this equation as xi times yi minus n times the mean of x times the mean of y. And these sum of squares, these formulas should look familiar from, I think, our introductory lectures. These sum of squares is related to the variance. And so the variance of x is the sum of squares of x divided by n. And that's where this is the population variance. And then the sum of squares of y divided by n is the variance of y. And then there's the what we normally call covariance. The covariance of x and y is the sum of squares of xy divided by n. And yeah, so this cove of xy is the covariance of x and y. And so we're going to use these definitions to derive our beta naught and beta 1 for the linear least squares for the simple linear model, bivariate case. Okay, and so this should be review from our last lecture, which we did on the whiteboard. We have for the simple linear model, we solve for y-intercept beta naught and the slope beta 1. It actually involves the matrix inverse of a 2 by 2 matrix, and then we multiply it by this vector. So we have a closed form analytical solution. And we can either keep it in the matrix vector form and just evaluate each one of these terms and do the matrix math, or there's actually then more of what I call the closed form analytical solution. Beta 1 then out explicitly equals this equation, and then beta naught is this equation. And so if we go back, so we take a look at the equation in this form, we go back to our definitions of sum of squares, we can rewrite, and this is why I put beta 1 first. Beta 1, the slope is simply the covariance of x and y divided by the variance of the inputs. Alternatively, it's the sum of squares of xy divided by the sum of squares of x. That's because the factor of 1 over n cancels here. But so the slope has a physical meaning. It's the covariance of x and y normalized by the variance of x. So the slope of the best fit line is the covariance normalized by the input variance. And similarly, we can do some of these substitutions and also some algebra, and you can work out this on your own time. We can rewrite beta naught is y bar minus beta 1 times x bar. And there's a physical significance of this is that the point representing the sample mean, x bar and y bar, so that's the mean of x and mean of y calculated from your data set that you used to build the regression model. it always lies directly on the line of best fit. And so if you rearrange this formula, bring the y bar over, or basically bring the beta 1, when you have a line of best fit, y equals beta naught plus beta 1 times x. If you put in x bar, you're going to get y bar. And so for the simple linear regression models, the line of best fit is constrained to pass through the sample mean point of the data set. And in the following lectures, we're going to give an explicit example of that. And so now we have, if you want to do the line of best fit, you can just calculate your sum of squares. That gives you beta 1, and then you already are going to have your mean values. You should already have calculated your variances anyways. When you collect data, you should automatically calculate some basic statistics to familiarize yourself with your data set. So you would have already calculated your y bar, x bar, and your variances, and perhaps even other statistical measures. And so here, you can go through the matrix math, or if you can just calculate these, and then you can get your line of best fit. So it's a little bit maybe faster for your programming. But of course, this only holds for the simple linear model.